So welcome to the second lecture of Statistical Inference. As you recall, in the previous lecture, we did population, random sample, and some more related definitions. Okay. So let's recall the key points again, because these are important for further study of random sample. So what's a population? Population is the collection of individuals' measurements or objects under study or consideration. What's a random sample? Random sample is a collection of n independent random variables from the distribution of a population. Say X follows some distribution with mean, mu, and variance sigma square. Then random sample is a collection of n independent random variables from this population distribution, such that each xi follows the same distribution as of x. Same distribution as of x. It means each xi has same mean mu and same variance sigma square. So again I repeat, random sample means a collection of n independent random variables from this population distribution. Okay. After that, what sample mean, that we denoted by x bar? It's 1 over n summation xi. I goes from 1 to n. So because x1, x2 are random variables, and it is a combination of random variables, it is again a random variable. So x bar is a random variable, and we learned that x bar follows a distribution with mean, mu, and variance sigma square over n. It's important to remember that x bar follows a distribution with mean, mu, and variance sigma square over n. Then we learned about sample variance. It's defined as 1 over n minus 1 summation I varying from 1 to n xi minus x bar whole square. It is again a random variable that follows a distribution with mean sigma square and variance v sigma square, where v sigma square has a formula like 1 over n expectation of x minus mu whole power 4 minus n minus 3 over n into n minus 1 sigma power 4. Okay. So x bar and s square are two statistics. By definition, what is a statistic? Any function of the random variables which are coming from random sample. Means sample based statistical measures are statistics, and population based statistical measures are parameters. So hope you recall these definitions. Okay, so this is what we learned in the previous lecture. These are important points that we have recalled. Now in today's lecture we will learn about sampling distributions. Means here we know that x bar follows a distribution with mean, mu, and variance sigma square over n. But what is this distribution? What is the nature of this distribution? What is precisely this distribution? That we don't know. Okay. So we will learn about the distribution of x bar and likewise some other important statistics. So now we will learn about sampling distributions of different statistics. Okay. So, before we learn about sampling distributions of different statistics, let's see some important results related to movement genetic function. What is the movement genetic function? Do you recall it? It's expectation of e power tx. Moment generating function of a random variable x by definition is expectation of e power tx. Now, if x1, x2 are two independent random variables, x1, x2 are independent random variables, and y equal to x1 plus x2, then what is moment generating function of y? Means sum of the two independent random variables. By definition, it should be e power t x1 plus x2. This can be written as e power tx1 into e power tx2. What does it mean? Expectation of the product of these two, e power tx1, e power tx2, but x1, x2 are independent random variables. That means e power tx1, e power tx2 are also independent. So, you know that result, if xy are independent random variables, then exy is equal to what? Ex into ey. You are aware with this result. So using that, you can write it expectation of e power tx1 into expectation of e power tx2. But what is first expression? Moment generating function of x1, and second is moment generating function of x2. So what we have learned from this result, that if x1, x2 are two independent random variables, then moment generating function of their sum is the product of their individual moment generating functions. This is very important result. Okay. Next, if y is linear combination, say y equal to a1x1 plus a2x2, linear combination of these two random variables, then moment generating function of y can easily be verified equal to moment generating function of x1 a1t plus moment generating function of x2 a2t. Note down this result. For linear combination, moment generating function is given by this product, not summation, it's product. Okay. Moment generating function of linear combination of two independent random variables is given by this expression. It can be extended to any number of independent random variables. All right. Now, there is a uniqueness property in moment generating function that you should know. Uniqueness property. What is it? If two random variables have same moment generating function, then they would have same distribution. If MGFs of two random variables are same, their probability distributions are also same. Okay. Let's see an example to understand this and use these results. Suppose x1, x2 are two independent random variables. X1 follows a normal distribution with mean mu1 and variance sigma 1 square. X2 follows a normal distribution with mean mu2 variance sigma 2 square. A1, A2 are any two constants. Let's determine moment generating function of A1 x1 plus A2 x2. For this, first you should recall the moment generating function of a normal random variable x with mean, mu, variance, sigma square. Hope you recall that. That is given by e power mu t plus half sigma square t square. Means x is following normal distribution with mean, mu, variance, sigma square. Then its moment generating function is given by e power mu t plus half sigma square t square. Okay, now let's see what's moment generating function of this linear combination myt. It should be mx1 a1t into mx2 a2t from our previous result. Okay, now what is mx1 a1t from this? It is e power, because x1 is following a normal distribution with mean mu1 variance sigma 1 square. So mx1t should be e power mu1t plus half sigma 1 square t square. Likewise mx2t e power mu 2t plus half sigma 2 square t square. So let's substitute those two here and multiply. What do we get? We get mu1 plus mu2 times t plus half sigma 1 square plus sigma 2 square t square. See it carefully. It is again matching with the moment generating function of the normal random variable. It means y follows a normal distribution with mean mu replaced by mu1 plus mu2 and variance sigma 1 square plus sigma 2 square. So we have a very important result now. What is that? Linear combination of independent normal random variables is again a normal random variable. Is that okay? Let's see how to use this result in the sampling distributions of different statistics. First, we will do sampling distribution of X bar. Here there are two possibilities. Maybe your random sample is taken from a normal population or non-normal population. So let's think about the first case. Suppose your random sample x1 to xn is taken from a normal population with mean mu and variance sigma square. Let's take this case. The random sample x1 to xn is taken from a normal population with mean mu and variance sigma square. What is x bar from it? 1 by n, by definition, 1 by n x1, 1 by n x2, and so on, 1 by n xn. We can write x bar in this format. But now what is it? It's a linear combination of independent normal random variables. So we can use the previous result to write its moment generating function. What is that? E power. If we apply that result, what do we get? Can you tell? If we apply that result, we get mu by n, how many times? N times t plus half. In place of sigma square, what will you write? Sigma 1 square, sigma 2 square, etc. You have sigma n over whole square, means sigma square over n square, and so on, n times sigma square n square. Yes. For each random variable, of course, the mean and variance are same. Okay. It is a random sample taken from this normal population. So each xi follows the same distribution. So mean for each random variable is same. Likewise, variance is also same for each random variable. Okay. So what do we get finally? Moment genetic function for x bar. We get e power mu t plus half n times sigma square over n square. That means sigma square over n. What do you conclude from this? It is clearly moment genetic function of a normal random variable with mean mu and variance sigma square over n. So make a note of this result. That sample mean follows a normal distribution with mean mu and variance sigma square over n. Here we have an important property that you should see carefully. Variance of x bar is sigma square over n. Let its normal distribution. The sample mean has same mean as the population mean. Variance is sigma square over n. So standard deviation is sigma over root n. So let's say here you have mu plus sigma over root n. This side mu minus sigma over root n. This is one sigma interval for x bar. Okay. Now, as I increase the value of n, what happens? The length of this interval, which is 2 sigma over root n, decreases. It means as we choose larger and larger sample, its mean value gets closer and closer to the population mean. Okay. All right. So we are done with the sampling distribution of x bar. And what is the concluding result? That x bar follows a normal distribution with mean equal to population mean and variance equal to sigma square over n, which decreases with the sample size. Okay, here we have taken normal population. What if the population is not normal? You have taken your random sample from, I'm discussing now second case, when the population from which random sample is taken is not normal. Not normal. In that case, we have a very powerful result which gives us the distribution of x bar called central limit theorem. Central limit theorem. In shortcut CLT. What it says, if a random sample x1 to xn is taken from a non-normal population, maybe normal also, with sample size greater than equal to 30, we call it large sample. Okay. So according to this theorem, if a random sample this of size equal to or greater than 30 is taken from a population, I'm not saying normal or non-normal, any population, then x bar follows normal distribution with mean mu and variance sigma square over n, where mu and sigma are the mean and variance of the population. But here it need not be exactly normal, it would be approximately normal. It would be exactly normal if the population from which random sample is taken is normal. That result we have already done in the previous case. Okay. So let's focus on the result. Suppose this random sample is taken from a non-normal population and random sample size is greater than equal to 30. This is a thumb rule for applying central limit theorem. Okay. So if the random sample size n is greater than equal to 30 and it is taken from a say non-normal population, any distribution with mean mu, variance sigma square, then x bar approximately follows a normal distribution with mean mu and variance sigma square over n. It means same result follows for non-normal population also for the distribution of x bar. Okay, but remember that for applying central limit theorem, the sample size should be equal to 30 or greater than 30. Okay, so even if the sample is taken from non-normal population, sampling distribution of x bar is normal. In this case, approximately normal with mean mu and variance sigma square over n. One more thing you should note down. If the population distribution is with some unknown variance, suppose variance is not given to you for the population, then also you can write this result that x bar approximately follows normal distribution with mean mu and variance s square over n. This time in place of sigma you can use sample variance. Okay. All right. So we have done the sampling distribution of x bar in case of non-normal population. Now, if the sample size is not large, means n is not greater than 30, n is less than 30, say, then what can we say about the distribution of x bar? If the sample size is not large, then what can we say about the distribution of x bar? So in this case, we have a special case. Suppose the sample is taken from a normal population, with mean mu and unknown variance. I'm just writing mu here. Because if variance is known, then that case we have already done. Okay. Suppose the sample is taken from a normal population with unknown variance. Then we have a result that you should write down, that the statistic x bar minus mu over s by root n. S is the standard deviation of your sample. Okay. This follows t distribution with n minus 1 degrees of freedom. Again, I repeat, a random sample of size n where n is less than 30 is taken from a normal population with mean mu and unknown variance. Then the statistic x bar minus mu over s by root n follows a t distribution with n minus 1 degrees of freedom. Let's accept this result without proof. Okay, it can be proved. All right. Then let's see the sampling distribution of a statistic involving s square, means variance of the random sample. In this case also we can say something in a particular case. Suppose the random sample is taken from a normal population. It is taken from a normal population with mean we don't need, you know or you don't know, it's fine, variance sigma square. The random sample is taken from a normal population with mean mu and variance sigma square. Then the statistic then the statistic n minus 1 s square over sigma square follows a chi-square distribution with n minus 1 degrees of freedom. Then the statistic n minus 1 s square over sigma square follows a chi-square distribution with n minus 1 degrees of freedom. This can also be proved. Okay, we will not prove it here. So this is the statistic that we can use regarding sampling distribution of S square. Okay. Now let us see some more useful statistics for which we will discuss sampling distributions. Finally, we will take up some examples. Sampling distribution of difference of sample means. Difference of sample means. Sampling distribution of the difference of sample means. Okay. Suppose two random samples are taken of size n1 and n2 from two normal populations with mean mu1 variance sigma 1 square, and the second random sample is taken from another normal population with mean mu2 and variance sigma 2 square. Two random samples of sizes n1 and n2 are taken from two normal populations with mean mu1 and variance sigma 1 square, another population with mean mu2 with variance sigma 2 square respectively. Okay. Let's say x1 bar denotes the sample mean of first random sample, x2 bar denotes the second. x2 bar denotes the mean of the second random sample. What I'm interested in to find the sampling distribution of x1 bar minus x2 bar. This difference is also a statistic based on these two random samples. Okay. So first of all, because x1 bar, x2 bar are sample means of two random samples taken from two normal populations, both are random variables. Correct? Both are random variables. And you know that linear combination of random variables is again a random variable. That means x1 bar minus x2 bar is a normal random variable. That is for sure. It follows a normal distribution. Now, what remains to determine? Its mean and variance. That's also easy to calculate. What is the mean of x1 bar? x1 bar follows which distribution? Normal distribution with mean same as population mean and variance sigma 1 square over n. Likewise, x2 bar follows normal distribution with mean mu2 and variance sigma 2 square over n2. In that case, n1, here n2. Okay. So, what should be mean of x1 bar minus x2 bar? You know this expectation rule. It is ax1 bar minus ax2 bar, means this should be mu1 minus mu2. And what is variance of x1 bar minus x2 bar? It is vx1 bar plus vx2 bar. So it becomes sigma 1 square plus sigma 2 square over n1 from here. Okay, vx1 bar plus vx2 bar. So x1 bar minus x2 bar follows normal distribution with mean mu1 minus mu2, and variance sigma 1 square over n1 plus sigma 2 square over n2. Okay. Difference of the sample means follows a normal distribution with mean mu1 minus mu2, variance sigma 1 square over n1 plus sigma 2 square over n2. Okay. Let's see the next sampling distribution. It is related to sample proportion. Sample proportion. Let's say you have a binomial population where probability of success in each trial is P. You know, binomial distribution is characterized by two parameters, number of trials and probability of success. Let's say in general, the success probability is P. After that, let's say n trials are performed and X successes are obtained. X successes in n trials. So this is your sample information from the binomial population. So what is the sample proportion here? Sample proportion success, or you can say sample success proportion. It is x over n. Let's denote it by p cap, p hat or p cap. So this is a random variable. The sample success proportion is a random variable because x is random here. Let's determine the sampling distribution of p cap. How to do it? First of all, we should know the nature of this random variable x. So you know binomial distribution can be approximated by normal distribution under certain conditions. You recall those conditions. If np greater than equal to 10 and p 1 minus p greater than equal to 10, under such conditions, x follows normal distribution with mean np, variance np into 1 minus p. Right? X is a binomial random variable initially. It's a random variable related to binomial population, but under these conditions, it can be approximated by a normal random variable with mean np, variance np times 1 minus p. Hope you recall these results that you did in earlier chapters. Okay? Now, from this information, let's think about the distribution of p cap. X is a normal random variable. 1 of x over n is simply linear combination of x. 1 over n is a constant. So this is again a normal random variable. X over n is a normal random variable. Means p cap also follows normal distribution with mean and p over n. That means p and variance np into 1 minus p over n square. You know, in variance constant gets squared. So you get p into 1 minus p over n. So it means sample proportion variable follows a normal distribution with mean p and variance p into 1 minus p over n. Make a note of this result. Sample proportion success random variable follows normal distribution with mean equal to p and variance p into 1 minus p over n. Similarly, we can think about distribution of difference of two sample proportions. Difference of sample proportions means this time suppose you have two binomial populations with success proportions P1, P2. Okay. Then you have done annual trials in the first population and you obtain X1 successes. From N2 trials in the second population, you got X2 successes. So sample proportion success in the first population is X1 over N1, second X2 over N2. We are interested to find the sampling distribution of P1 cap minus P2 cap. So let's say these x1, x2 satisfy those normality conditions, means x1 follows a normal distribution with mean n1 p1. X1 follows normal distribution with mean n1 p1, variance n1 p1 into 1 minus p1. Similarly, x2 follows normal distribution with mean n2 p2, variance n2 p2 into 1 minus p2. Now, what is distribution of P1 cap minus P2 cap? As we have done in the single sample proportion case, x1 over n1 follows which distribution? Normal distribution with mean P1 and variance P1 into 1 minus P1 over n1. Likewise, x2 over n2 means P2 cap follows normal distribution with mean P2, variance P2 into 1 minus P2 over N2. So you know the distributions of P1 cap and P2 cap. Both are normal. What does it mean? The difference is also a normal random variable with mean P1 minus P2 and variance with mean P1 minus P2 variance. Can you tell variance from this? Just addition of these two? Yes. If this is sigma 1 square, this is sigma 2 square, then variance of this is sigma 1 square plus sigma 2 square, just addition of these two. But mean is P1 minus P2. Okay. All right. So we are done with different types of sampling distributions. Now let's do a couple of examples. After listening the statement of the example, you have to understand which sampling distribution it is related to, and accordingly you need to solve it. Okay, listen the first example. The breaking strength of a rivet. The breaking strength of a rivet. Rivet, you understand? a nail that holds two metal sheets together. A nail that is used to hold two metal sheets together, to join two metal sheets. Okay, so the breaking strength of a rivet has a mean value 10,000 psi. It is a term related to civil engineering, okay? And standard deviation means sigma 500 psi. The breaking strength of a rivet has a mean value of 10,000 psi and a standard deviation of 500 psi. What is the probability that the sample mean breaking strength for a random sample of 40 rivets, n is 40, is between 9950 and 10250? Means find the probability of x bar lying between 9950 and 10250. So first identify this problem. It relates to which kind of sampling distribution? Which kind of sampling distribution? See, nature of population distribution is not given to you, but you can look at the sample sizes. It is greater than 30. It is greater than 30. So what can you apply in this case to determine this probability? The central limit theorem. Okay. So by central limit theorem, x bar approximately follows the normal distribution. X bar approximately follows the normal distribution. So you can use that thing by central limit theorem. It is approximately probability of 9950 minus, just change it into the standard normal variable. 9950 minus 10,000 divided by sigma by root, and that means 500 over root 40 less than equal to jet x bar minus mu over sigma by root, and that becomes standard normal variable less than equal to 10250 minus 10,000 divided by 500 over root 40. Now simplify it further. You should get minus 0.63 less than equal to z less than equal to 3.16. So it is the range of a standard normal variable. You can change it to capital F, the CDF of standard normal variable, and you can write it 3.16 F 3.16 minus F minus 0.63. These two values you can see from the table and calculate the difference. The values from the table are 0.992 minus 0.2643. Please check from the table. 2643. Final answer you get is 0.7349. Okay. So in this problem we have applied this central limit theorem. Why? Because the nature of population was not given to us, but sample size is greater than 30. So we have used central limit theorem to find this probability of the sample mean. Okay. Let's do one more problem. The problem is an electrical firm manufactures light bulbs that have a length of life that is normally distributed with mean mu equal to 800 hours. Population is normal. Mean life of the light bulbs, electric bulbs, is given to you equal to 800 hours. Okay. Find the probability that a random sample of 16 bulbs, mean size is 16, with a standard deviation of 40 hours. Standard deviation 40 hours will have an average life of less than 775 hours. Means you need probability x bar less than 775 from this information. Population is normal, it is given to you, normal population. Life of the electric bulbs is normally distributed with mean 800 hours. A random sample of size 16 is selected with standard deviation 40. Then you need to determine probability x bar less than 775. So first thing is that you should identify the proper statistic to deal with this probability. Population normal, sample size less than 30. Small sample, normal population with unknown variance. See this, variance of population is not given to you. So which is the suitable test statistic in this case? Yeah, t distribution. In this case, you can apply t distribution. So if you change x bar to t, how it reads? It reads t15 less than minus 2.5. Recall that relation. T statistic with n minus 1 degrees of freedom is x bar minus mu over s over root n. So just put here x bar equal to 775, mu 800, and 16 as 40, you will get minus 2.5. Okay, this value you can see from the t distribution table, and you will find it 0.0123. Actually, t distribution is also like normal distribution. It is symmetric about t equal to 0. So you want to find this probability less than minus 2.5. Because of symmetry, this probability is also the same that you need here 2.5. So in the table you can see probability greater than 2.5. You will find it. Okay. So we have done some examples based on the sampling distributions. You can practice more examples from your side. Now, let's see what are classical methods for statistical inference. Classical methods for statistical inference. There are three methods that we will study for statistical inference. Let me tell you briefly about these methods one by one. First classical method for statistical inference is point estimation. What does it mean? In this method, we use the sample information to estimate the corresponding population parameter. In this method, we use the sample information to estimate the value of the population parameter directly. Okay. Second, confidence interval. In this case, we use the sample information to determine an interval with certain probability where the population parameter is supposed to lie. We do not give the value of the population parameter, rather we tell an interval which we call confidence interval. We tell an interval in which the population parameter is supposed to lie. Okay? Think like this. Let's say you want to estimate population parameter mu using the sample information, means using X bar. So suppose we have some method which gives direct estimate, for mu. This is point estimation. For the value of mu, it gives direct estimate. In confidence intervals, we do not have the direct value of the population parameter. Rather, we tell some interval, say L1 to L2, with certain probability where mu lies, where the population parameter lies. Okay, that we call confidence interval. Third is hypothesis testing. Third is hypothesis testing. What is it? In this case, there is an existing statement or hypothesis about the population. There is an existing statement or hypothesis about the population, which we denote by H naught and called null hypothesis. You will see it later. Just I am telling you very briefly what hypothesis testing is. So there is an existing statement about the population parameter, say mu. In hypothesis testing, what we do, we employ some statistical methods which check whether this H naught statement or the prevailing statement about the population parameter is true or not. We test the prevailing statement about the population parameter using the statistical methods in hypothesis testing. Okay, so these are three methods that we will learn one by one in detail. So let's move further and see the methods of point estimation. In point estimation, first let's see the meaning of unbiased point estimator. A sample-based measure or a statistic theta cap is said to be unbiased point estimator for a population parameter theta if the expected value of theta cap is theta. A statistic theta cap is unbiased point estimator for the population parameter theta if expectation of theta cap is equal to theta. That okay? You are familiar with the unbiased point estimator. See this. Expectation of X bar is what? Mu? Mu is the population mean. That means X bar works as unbiased point estimator for the population mean mu. Similarly, expectation of S square is sigma square, population variance. It means sample variance is unbiased point estimator for population variance sigma square. Now you understand why we defined S square with division by 1 over n minus 1 instead of n. Because if we divide by n minus 1, we get unbiased point estimator. for the population variance from S square. Okay. So this is unbiased point estimator that we denote with the cap symbol. Now let's see the methods of point estimation. First method, that is method of maximum likelihood. Or in shortcut we can say maximum likelihood method, ML method. What is in this method? We write a likelihood function. We write a likelihood function that gives the probability of our sample. We write a likelihood function that gives the probability of our sample. Suppose the parameter that is to be estimated is theta. Okay. So L theta is a function that will give you the probability of your sample. Main thing is that you need to write a function that gives the probability of your sample. After that, maximize the likelihood function to get an estimate for theta. Why? Why do we need to maximize? Because this gives the probability of sample. Sample you have obtained. Sample is the true thing. So this function should give the probability of your sample to the maximum value. The value of theta for which L theta is maximum gives the maximum probability of your sample. Okay, so this is the principle behind this method. Again, I repeat, L theta is the function that gives the probability of your sample. Sample you have obtained. So sample data is the true thing, that is 100% true. Okay. So to get the maximum probability of your sample, this function should be maximum. So likelihood function is the probability of the function that gives the probability of your sample. You need to maximize it. So the value of theta for which it maximum, that is an estimate for your population parameter theta. Okay. Let's see an example to understand it. Example 1. Suppose a coin is tossed 7 times. No, a coin is tossed, say 10 times, and 7 times head appears. A coin is tossed 10 times, and 7 times head appears. Let P denotes the probability of success in any trial. Let P denote the probability of success in any trial. Means it is the parameter of your binomial population. You understand this situation is governed by binomial distribution. Okay. So P is the population parameter. So from this sample information, let's estimate the value of P. So the problem is, I repeat the problem again. A coin is tossed 10 times, 7 times head appears. Let P denote the probability of getting head in each trial. So this is the probability of success in the population. Estimate the value of P using this sample information by maximum likelihood method. Now how to do it? First, you need to write a function that will call likelihood function that gives probability of getting 7 ads out of 10 trials. So what is that function? You know from binomial distribution, probability of getting 7 ads out of 10 trials is p power 7 into 1 minus p power 3. This is clearly a function of p. So this is the likelihood function of getting your sample. Correct? After that, what is the next step? We need to maximize it and find the corresponding value of p. So put its first derivative equal to 0 with respect to p. But before that, it would be convenient if you change it to logarithm on both sides. ln LP equal to ln 10c7 plus 7 times ln p plus or minus next. No, plus 3 times ln 1 minus p. Yes. Okay, differentiate it both sides with respect to p. What's right hand side? 0, 7 over p minus 3 over 1 minus p. Or maximum minimum, what to do? Put this derivative equal to 0. See what is the value of p. What is the value of p from it? Is it 7 by 10? Yes, it is 7 by 10. So this is the point estimate of p from ML method. Using the sample information, the point estimate for p from ML method is 7 over 10. Okay. Also, you can think directly, getting 7 ads out of 10. So success probability is 7 by 10. Okay, so we are done with this example. Let's see the next example. Example 2. Suppose 15 buses arrive on a bus stop in a span of 3 hours. 15 buses arrive on a bus stop in a span of 3 hours. Find the ML estimate of the average number of buses that arrive on the bus stop. Find the ML estimate of the average number of buses that arrive on the bus stop. So let lambda denote the average number of buses. So what is the probability of getting this sample information? Which distribution is applicable in this case? Poisson distribution. So what is S here if you want to apply Poisson? Do you recall the PMF of Poisson distribution? It is Fx equal to lambda s power how much? Okay, I'm writing the denominator. It is x factorial lambda x power x into e power minus lambda s. Okay, x goes from 0, 1 to 3 and so on. Here what is s? 3? S is 3, X is 15. Okay, so write the likelihood function of lambda. Likelihood function in terms of lambda for your given sample. This is 3 lambda power 15 e power minus lambda. S means minus 3 lambda over 15 factorial. Okay, do it further yourself. Take logarithm on both sides, put the derivative equal to 0, and see finally which value of lambda you get. If you put its derivative with respect to lambda equal to, not its derivative, its logarithmic derivative, derivative of ln L lambda equal to 0. See what do you get. You should get something like this, 15 over lambda minus 3 equal to 0. From this, what is lambda? 5. So ML estimate of lambda is 5. It means on an average 5 buses arrive on the bus stop per hour. Average number of buses arriving on the bus stop is 5. Okay. Alright, let's see one more problem. Where you will need to estimate two population parameters. Suppose a random sample x1 equal to a1 and so on xn equal to an is taken from a normal population with mean mu and variance sigma square. Here random sample values are given to you a1 to an. A random sample of size n is taken from a normal population with unknown mu and variance sigma square. Find ML estimates of mu and sigma square from this sample information. Okay. So the thing is that how to write the likelihood function of your sample. So what is the probability of x in normal distribution? Do you recall the density function, the probability density function of normal random variable? It is 1 over sigma root 2 pi e power minus half x minus mu over sigma whole square. Okay. So what is the density for say x1, x2 and so on xn? In general for xi it is this. So what is the density of these independent random variables x1 to xn jointly? Just multiply these n densities. Okay. So you get your likelihood function. If you multiply all these, what do you get after multiplication? Power n and e power each time added. So what do you get? E power minus half summation xi minus mu over sigma whole square. Now xi values are given as ai, so you can replace these by ai. I goes from 1 to n. So this is your likelihood function for mu and sigma. AIs are given to you. So right hand side is a function of mu and sigma. Now what is the next step to determine or estimate mu and sigma? Take logarithm on both sides, that would be helpful. Take logarithm on both sides, then put partial derivatives of ln L mu sigma with respect to mu and sigma equal to 0. Because it is a two variable function, so to find maxima, you need to put its partial derivatives with respect to mu and sigma equal to 0. Okay, do those calculations yourself. I'm writing here the final answer that you will get. You will get mu equal to summation ai I from 1 to n. 1 by n summation ai I from 1 to n. And sigma square turns out 1 over n summation I varying from 1 to n ai minus ai minus a whole square. So these are your ML estimates for mu and sigma square. Okay. So main thing in ML method is that you need to construct a likelihood function that gives the probability of your sample. So it depends on the problem. Okay. I have done here 3 examples. Similarly, you can practice more examples. Okay. Now let's see the second method for point estimate of the population parameter. Second method, that is the method of movements. So in method of movements, what we do, one side we have population random variable movements. You know E x power k. This is kth movement of the population variable x. This side you have population. That side it is sample. Now you should know how we define sample moments. Sample moments, kth sample moment is defined as 1 by n I varying from 1 to n. Let's say you are choosing a sample of size n. Then sample moment is 1 over n. Kth sample moment is 1 over n summation I varying from 1 to n xi power k. Xi power k. Okay. Kth moment of the population random variable is E x power k, expectation of x power k, and kth moment of the sample x1 to xn is 1 over n summation I varying from 1 to n xi power k. Okay, so to estimate the population parameters, we equate the two moments. Let's see an example. Listen the example. A forester plants 5 rows of pine seedlings. 5 rows of pine seedlings. A forester plants 5 rows of pine seedlings with 20 pine seedlings in each row. With 20 pine seedlings in each row. Let X denote the number of seedlings per row that survive the first winter. X denotes the number of seedlings per row that survive the first winter. Okay. Then X follows a binomial distribution. X follows a binomial distribution with mean with n equal to 20 and say some unknown p. Find an estimate of P given that a random sample x1 equal to 18, x2 equal to 17, x3 equal to 15, x4 equal to 19, yes 19, and x5 equal to 20. Why x follows a binomial distribution? Because a point seedlings either survives or not. There are only two possibilities for any x. So it follows a binomial distribution. Suppose survival probability is p, that we don't know. N is given 20. After that, a random sample is given with 5 values 18, 17, 15, 19, and 20. From the sample information, estimate the value of p. So what is the population movement here? X is a binomial random variable. Population movement, first movement is what? If X is binomial random variable, first movement is NP. Expectation of X, mean of the binomial random variable. N is given to you, so it is 20p. Okay. From the sample, what is the first movement? There are 5 entries. 1 over 5 summation xi means 18 plus 17 plus 15 plus 19 plus 20. How much it is? If we calculate, we find it 17.8. Okay, so this is first movement from the population. This is first movement from the population, and this is the first movement from the sample. Let's equate the two to get an estimate of P. What do we get from it? P equal to 0.89. So this is the moment estimate for P. Okay. This is the moment estimate for P. Alright, let's see one more example. Example 2. Suppose 2, 4, 3, 6, and 10. 2, 4, 3, 6, and 10 are the values of a sample of size 5 from a gamma distribution. Means a sample of size 5, values are given here, constitutes a sample from a gamma distribution. Find the estimates of the parameters alpha and beta of the gamma distribution. You know, gamma distribution is characterized by two parameters, alpha and beta. So here what you need to recall from gamma distribution? Moments, first moment and second moment, because there are two parameters to be estimated, so you need two equations. One side find population moments, other side sample moments. Sample is given to you, so you can write easily sample moments. First moment is 1 over 5, addition of these 5 numbers, 2 plus 4 plus 3 plus 6 plus 10, equal to how much? 5? Yes, 5. And the second sample moment is just add the square sum. How much you get? Can you calculate it? In the meantime, I recall the moments from the gamma distribution. First moment is simply mean of the gamma random variable. You're telling 33. I don't know. You just check it, okay? All right. So EX, first moment, or you can say mean of the gamma random variable. Do you recall what's it? It's alpha beta. And second moment is how to recall second moment. If you know variance, then it's easy to recall. Because you know this relation that variance x equal to ex square minus ex whole square. So variance is alpha beta square. So from this you can write second moment. Second moment is alpha beta square plus alpha square beta square. Okay. Now, first moment from the population is alpha beta from the sample is 5. Second moment from the population is alpha beta square plus alpha square beta square. From the sample is it is 33. So tell me the values of alpha and beta. So these are the estimates from this method for alpha and beta. Okay, put alpha beta equal to 5 here. What do you get? 25. If I put this is 25, then what are alpha and beta finally? Check it. Hmm? It is 25 means 8. Yes, it's 8 over 5. Beta equal to 8 over 5. Yes. And alpha? Beta is 8 over 5. Alpha is 25 over 8. Okay. So hope you have understood this method of moments. If you need more than one population variable to estimate or population parameter to estimate, then write more than one equation. Okay. From the moments of the sample and the moments of the population. All right. So we are done with the one classical method of statistical inference, that is point estimate. But before I finish, I want to tell the difference between two terms. One is estimate and other is estimator. What is the meaning of estimator? It is the random variable that estimates the population parameter. Okay, and its value, let's denote it by x bar. Its value is the estimate for the population parameter. Okay, estimator is a random variable to estimate the population parameter, and its particular value is the estimate of the population parameter. All right, so as I said, we are done with the first method of statistical inference, that is point estimate. Next time we will do confidence intervals. Thank you.